This is Linked Data Engineering, lecture number 3, Linked Data Vocabularies and Ontologies. In this part of the lecture, we want to talk about linked data vocabularies. Okay, assume the following situation. You want to define personal data for a user or a person, which means you want to define a given name, a last name, some address-related data like the street or the town, the place where the person lives. You want to give the definition of a web page, the email address, and so on and so on. Okay, now no big deal. There are several possibilities how you are going to do this with linked data. So first of all, of course, you could define a new vocabulary completely according to your needs. The point is then, your vocabulary is only a good thing if it's also used by others and if others can understand it. So possibly you should look whether there exists already a vocabulary that is somehow fitting to your needs. So the next thing would be, I use an existing vocabulary and possibly adapt my application accordingly to these vocabularies. But on the other hand, you could also use an existing vocabulary and extend this vocabulary. This is the nice thing in linked data. There is an open world. We will talk about this. Linked data follows an open world assumption. So we use existing vocabularies and extend these vocabularies according to our needs. So we put something in there which has not been there. So we do some refinement, some add-on and stuff like that. So this is possible. 3 possibilities: define new, use existing and adapt your application, or use existing and extend the existing vocabulary. Okay, example. We have already talked about the friend of a friend vocabulary. This is usually used to describe persons, their activities, their relations to other persons and objects. I have here put also the link to the FOV project web page here, so you can click on it and have a look at it and read more information about exactly this kind of vocabulary and how it can be used. Here is a typical FOV file, so it's a FOV profile it is called. It is written here again in RDF Turtle, and you see here we are using some prefixes like RDF, RDFS and up, but also of course the FOV namespace. And then I'm talking in this file about me. So this file contains information about me, but if I want to refer to me as a subject, I of course use the URI of this file and then hash me, which then is the subject. And then I can say I am a person, according to I belong to the class FOV person. Then I have a name, I have a mailbox, I have a homepage, there is a depiction of me, I have several interests and stuff like that. And I know, of course, another person who is Magnus, one of the tutors of this course. This can be perfectly expressed with FOV. Yeah, so where can I find such nice vocabularies as FOV? There is a rather prominent website which collects all available, all valid linked data vocabularies. And this is the Linked Open Vocabularies website. Here is a graph of all the available vocabularies and about their usage, how often they are used. So the size of the bubble somehow corresponds to their usage. So DC terms, we have also learned about this. This is the Dublin Core vocabulary, is a rather prominent vocabulary, but also the FOV vocabulary is really prominent. Let's have a look at this website, because this will be the starting point where you will be looking for vocabularies. So this is the vocabulary, and you see here, it seems not to be such a big number. There are 576 vocabularies in linked open vocabularies listed. Now, let's try it out. We want to look for a vocabulary that can be used for persons. Let's try person. Okay, we are looking for person, and of course the most prominent hit here will be FOV person, but there are also other kind of vocabularies that you see here. And you see also in the definition, the person class represents a single person entity. This could be also used. Or here you have here BBC core data also has person. There is a sports ontology or sports vocabulary which also contains person. And here you have schema.org, which is also, of course, a vocabulary for which an RDF representation exists. And there is also a person. And here, of course, a person can also be alive, dead, undead, that's interesting, or fictional. So you see, and then you can select which kind of person you want to use. So you could look what kind of attributes are used, what kind of properties are used for this in this vocabulary, if this is fitting to you. Let's look for something more exotic. So for example, for a space mission. So I look for space and I see here space mission. There is something, so I can click on it. And you see here, okay, in the DBpedia ontology, there is space mission. That's quite interesting. And also we have here something which is a space mission, and we can see here in the comment, any mission in space in which space shuttles or spacecrafts are involved is a space mission, and so on and so on. And we see here further down, this is not necessarily a space mission. But if these two already fit to my needs, I could select them, or I can click on them and then I can further explore this data. So I also recommend to you to play around a little bit with this linked open vocabularies to get to know all the vocabularies and to learn more about the usage and the content of these existing prominent vocabularies that you can use for your applications. Okay, this was the question where to find linked data vocabularies. Now, sorry, it can happen that, for example, you are using a vocabulary, but probably not using it in the correct way it was intended to. Let's look at the following example. You have here the property FOF publications, and this is defined in the FOF namespace with the domain person and the range document, which means a person can have documents which are the person's publications. Now let's have a look at the following data I define here, or I have here as a subject in my RDF data, the Hasso-Plattner Institute, which is of type organization. And then I say, okay, also the Hasso-Plattner Institute has publications, and then I list here a publication which belongs to the Hasso-Plattner Institute. Yeah, now this is tricky, because if you look at the domain range restriction that is already there, the question here is, of course, is a FOF person the same as DBO, so the DBpedia ontology organization? Are they somehow compatible? I don't know. That's, of course, some difficulty that we have to solve. According to RDFS semantics that we have already known, so we have here FOF publications has the domain FOF person, it can be deduced that Hasso-Plattner Institute also is of type FOF person. And the interesting thing is, RDF doesn't care. It can be both. So Hasso-Plattner Institute can be an organization as well as be a person. And the person is simply deduced by this implicit knowledge given by the domain definition of this property publications. And the reason why both can stand there and don't hurt each other is that RDF, as all the other languages in the semantic web and linked data domain, are following an open world assumption. What's an open world assumption? Okay, let's look at the following problem. So the open world assumption, OWA. Here in the blue box, you see our knowledge base. What is in the knowledge base? It's simply expressed here in natural language. It says a sheep is an animal with 4 legs. Now we ask the following question. Can sheep fly? Good question, you might say. But according to our knowledge base, we can't say. In an open world, you have no idea, but probably, of course, sheep could fly, according to our knowledge base, because there is no contradictory statement. Under the open world assumption, unless we have the statement or we can infer the statement that sheep can or cannot fly, we have to return the answer, we don't know, possibly yes. This is completely different in a closed world. In a closed world, usually the leg of existence of some information is interpreted as its negation. It means then if the information is not there, it means the negative of the information holds. In a closed world, we could say no, sheep cannot fly because our knowledge base says sheep has 4 legs, but not that it can fly. But we are following an open world where everything is possible unless we state the contrary wise. In a real world, of course, we are used to deal with incomplete information in our everyday life. So this is quite normal for us. So therefore, also here in the semantic web and in linked data, we are following an open world assumption, which also has some other benefits. So in the semantic web and linked data, we expect people to extend our own models. So a vocabulary, for example, if you find it, you extend it according to your own needs. So it means the person who is defining first the vocabulary does not have to worry in advance about every possible extension to cover everything with his or her vocabulary. This is the nice thing about semantic web and about the open world assumption. You model something and you know, of course, it's underspecified. It's not necessarily complete. It's incomplete by default. But who cares? If it's perfect for your application, do it exactly that way. If another one is reusing it and simply is stating, oh, there is something missing, I have to add this and this and this and this, then of course he can add it. It's no problem, no big deal to complement this information. Therefore, we can intentionally underspecify our models and allow others to reuse them for extension. This is the reason for the open world assumption. So, for example, we can extend also our existing knowledge base that we say a sheep is an animal with 4 legs that, if lifted, can fly. Then we can answer, yes, of course, sheep can fly. So this is the open world assumption. But nevertheless, we have some problems we have to deal with, because RDF and RDFS not is really sufficient for every task we want to follow here. So for example, if you have the following definition, if you say an animal eats food, so you have a property which is called eats and that has the domain animal and the range food, and you say, okay, food consists of the subclasses vegetables and meat, so these are 2 subclasses of food, and there might exist, of course, also other kind of food. Now the problem is, if you want to say a cow eats only vegetables and want to make a cow an animal, it's probably difficult to define this based on that model. Also, if you then define other animals, members of the same class, and say they eat only meat or they eat both meat and vegetables, it's difficult. So this is called the problem of locality of global attributes, and therefore you need some way to make a distinction, to do refinements, and this is not possible in RDFS, so therefore you need here more semantic expressivity. Another case we have already heard of is here, for example, the possibility to express disjunctive classes. If you want to define women as a subclass of human and man to be subclass of human, we possibly want to make these 2 classes disjunctive, meaning that there exists no individual which is at the same time member of both classes. So therefore these 2 classes are disjunctive. RDFS subclass relation cannot express exactly this thing. So therefore, we need more semantic expressivity. Another example, if I want to define more complex classes, classes which consists of the content of other classes, for example, here I define road users, which consists of motorists, motorcyclists, pedestrians, and cyclists. If I define it in exactly that way with RDFS, of course, there can be also other things which are road users and which are not here referred to in the subclasses. So this exclusivity, if I say the new class contains only members from the given class combinations, this is not possible. Again, missing semantic expressivity for class combinations. And this we have also already heard, cardinality constraints. If I want to define parents and I want to say that every human usually has 2 parents, in RDF and RDFS I only can say that human has a parent who is of class parent, and I also can say that parent is a subclass of human. But this cardinality constraint that, for example, each human usually has 2 parents, I can't express that. What else? of course, there can be special kind of property constraints, like, for example, transitivity. What is transitivity? Take, for example, the property is greater than. You can define numbers, for example, A is greater than B, and you can define B is greater than C. But according to the transitivity of this relation, this also means that A must be greater than C. But to define that a property has to be transitive, this is not possible in RDFS. It's the same with uniqueness, that you say, okay, everybody usually only has one mother, and the mother is unique, which means this is kind of a functional property. This is also not possible to define. Likewise with the inversiveness. Inversiveness of properties means you define a property like is parent of, and you have another property is child of, and you say, yeah, these two properties are inverse, simply because if A is parent of B, then B is child of A. So this is an inversiveness relationship between two properties, and you want to state that. And to state something like that is really important to express semantics, and also the machine must understand that these two properties somehow are related. We can't express that. And an even more severe problem, the general problem of RDFS, is that RDFS does not have the possibility of negation. If I define the two RDF triples that state that I am of type vegetarian and I am of type non-vegetarian, this does not automatically generate a contradiction, simply because also of the open world assumption, and we have not the possibility here in RDFS to express that something is a negation of another thing. Both things hold at the same time, so this does not generate automatically a contradiction. Now, this is a bad situation, of course, but of course there are remedies and means to cope with that. And in the next part of the lecture we will learn about OWL, which is the web ontology language, which gives us the mandatory expressivity that we need.